All right. I don't want to waste any time, so I got like 30 minutes. I'm streaming. Let's on gate, shall we? All right. Where are we in the subjects? All right. Let's continue. Regarding the discrete mathematics. Okay. Where are we, people? Okay, we didn't solve a lot of questions. Absolutely. We did that. We did this. All right. This one, like abelian monoid, abelian group question, we were stuck at there. Yeah, this one. So I felt sleepy and then I slept for some time and then I, woke up and then I went to bazaar and then I came back now and I need to take bath. Anyways, let's solve like, 20 is too much. Wait, let's solve like 10 questions and then I will go take a bath. And then we will come back again. What do you say? So I have already done this question. Alright. What is a group? What is a monoid? What is abelian? And non-abelian. I did not study the group theory, that's why I didn't remember that. I mean, they were not in our syllabus, but that's alright. Okay, group is closure, associative, identity, and inverse. Okay. Closure, associativity, identity, that is a group. It is a monoid, yeah. Monoid plus inverse is equals to group. And abelian, I think commutative also adds up, right? Abelian commutativity holds. I mean, if you do some problems, all right. If you look at this, all right, commutative is holding. That's why it is abelian. And in that, do we have closure? Since they are non-negative integers, yes, we have closure. We have associativity. Yes, we have associativity. We have identity. I mean, yeah, identity is addition. But since it is positive, we do not have an inverse. Anything except 0 does not have inverse, so it is not a group. It is an abelian monoid. It is an abelian monoid. B abelian monoid, yeah. That checks out. Okay, on to the next question. P and Q be the following propositions. Fail grade can be given. Student scores more than 50% marks. So the statement fail grade cannot be given which the student scores more than 50%. If students score more than 50% of marks, then fair grade cannot be given. That's it, right? That's it. Q inverse negation. PA is your answer. Right. Wow. Yeah, answer is A. We are good. If you know the theory, it is real easy. AB and adjacency matrix of simple undirected graph, okay? Suppose A has its own inverse. A has its A. Okay, A is its own inverse. So when is A is equals to A inverse? Alright, adjoint of A by determinant of A is equals to A inverse. So this is saying that is equals to A. So if adjoint of A is equals to A, then determinant is equals to 1. Determinant of A should be 1, right? Why don't we do that? Okay, that should be 1. When will that is 1? You need to have a deep understanding about linear algebra for this one. Okay, he wrote, what the heck? Okay. No, why are these people writing these huge questions? Okay. I'm lacking a lot of theory to solve this question. So when is A equals A inverse? And what is a cycle? Perfect matching and complete graph, and how to get the connection between linear algebra and graph theory. Okay. A is equals to A inverse. Alright, my bad. A by A inverse is equals to identity. So A square is equals to identity. Okay. Cycle is a closed path where vertices are distinct. Cycle is a closed path where vertices are distinct except for the first and last one. Okay. That is how you define it. So this is a cycle A, B, D, C, A, except for the first and last one, all the others are distinct. Good. Okay, perfect matching is a set of edges with no shared vertices. Okay, perfect matching. A, B, C, D form the perfect matching. A complete graph has every pair of distinct vertices connected by an edge. Yeah, I know that. 1, 2, something like this. It will be something like that, yeah. Algebra and graph theory. Adjacency matrix for a graph with n vertices defined by n matrix where there is an edge at 0. The entity a power k gives the number of walks of length k from vertex I to vertex j. Reveals structural properties like connectivity, bipartiteness, and expansion. Okay. The permanent of adjacency matrices counts perfect matching. Wow. So now let's solve this question. Radii be an adjacency matrix. For simple undirected graph, asymmetric. Loops. Okay, for a simple okay. So if you were to draw, alright, you do this. A B C D A B C D. There is no edge from AB. Similarly, it will get diagonal matrix. Got it. A square AG equals to number of two walks. It's exactly the degree. He did something. He did some sort of analysis. Okay, let me get this right. I was able to Alright, this is a one more question. Wow. So it is a direct theorem until the diagonal element 0 part. Can you explain the other things, please? So we don't know enough graph theory to solve questions. Okay. But when we compute a square, the diagonal entities are not necessarily 0. They count the number of two-step walks that start and end at vertex I. Maybe A to B, A to A to B, A to C, to D, that's 0. Alright. B to A, B to B, B to C, B to D, that's 1. C to A, C to B, C to C, C to D. D to A, D to B, D to C, D to D. This is our, what do you call? This is our matrix. And if you look at it, it is symmetric. A13, A31, yeah, A24, A42. It is symmetric, alright. That checks out. I mean, an edge goes. So if I were to compute a square for this one, should I compute a square? Will I then get an idea? Um, B to A, B to D, C to D, yeah, that works out. Zero times zero, right? Computing, that's tough. There got to be an easier way than that. For vertex I, alright. They are not necessarily to be zero, yeah. They will count the number of two steps walks that start and end at vertex I. For vertex I, a two-step walk was IJI. Okay. You idiot, this is not a simple graph in the first place because it is cyclic. So a simple graph looks something like this: A to B, A to C, B to C. That is a simple graph. Now, A to B and A to C, there is no A to D. B to A and D, C to A only, this will be 0. And D to C, this will be 0 as well. This is our new adjacent matrix representation. A two-step walk. One step, two steps. Okay, there is only the number of such walks equal to the degree of vertex I. This might seem stupid, but what is degree? Sorry, our exams. Or the number of edges incidents on it. The number of connections it has. Okay. So, a perfect matching is not a connected graph, right? That does not guarantee connectivity. Yeah. The graph has more edges beyond matching. Yeah, that made sense. Okay. That made the terminology clear for us. Let's consider a graph with edges A, B, A, C, and B, D. It is simple and undirected. I have written the adjacent matrix for that one. What is the next step? Right. Okay. Okay. Yeah, that is correct. Number of two-step walks. Number of two-step walks is equals to A square I. The number of two-step walks is this, or 2, so that is degree. So the condition A has its own inverse is not satisfied for the graph that I given. Okay. All right. Since we had A square is equals to I, is possible only when the diagonal elements are 1. Diagonal elements essentially give the degree. Do they? are equal to 1 in A square. Since it is simple graph, initially ai is equals to 0. So a square ii should be 1. Now it will be 1 only when the two length box is equals to 1. Two length box is equals to degree. So every edge has degree 1, which is perfect matching. Alright. Okay, so yeah, this reasoning is important. Adjacency matrix. Okay, what did I do? I did determinant and all. A simple graph means I is equal to 0. Condition a square is equals to I, since a is equals to a inverse. So a square I should be 1. A square ij, I not equals to j, is equals to 0. Alright. Diagonal elements. A square counts number of two-step walks. Two-step walks is equals to degree. So degree for every vertex is equals to 1. That is perfect matching. Disjoints at union. Okay, we made it. How many questions did we do? 1, 2, 3. 3 questions we did. That's it. 3 questions in 30 minutes. Wow, each question took 10 minutes. Yeah. But it is very worth it. Partial order. Okay. X belongs to 1 to the 4. The brackets are not matching. Okay. XX union 1, 2, 3, 2, 3, 4. The total number of orders that contain P. The number of total orders. So let's do this. It will be 1, 1, 2, 2, 3, 3, 4, 4, and 1, 2, 3, 2, 3, 4 are partial orders. So what are total orders now? I don't know what total orders are. What are total orders in this context? Hmm. Total order means linear order. I see. Comparability. Okay, draw the Venn diagram. Okay. How do you draw a Venn diagram for ordered pairs? Grind. Visual representation of partial order means minimal comparability without transitive shortcuts. Okay. One and one are not equal. One, two, two, three. That's it. Three, three, four, four, one, four, one. No idea. Yeah, I got this much. Now the different total order. Okay, we only studied partial orders. We did not study total orders. We will do that. Undirected connected graph. In which every edge has a positive integer weight. Spanning tree has even weight. No, this is not true. Two odd weights can make up an even weight. Undirected connected graph. It is not told simple. 1, 2, 1, 2. Every spanning tree. This is a spanning tree. It has even weight, but they just have odd weight. This is a spanning tree. This is a spanning tree. This is a spanning tree. Oh, wait. Oh, wait. This is a spanning tree, but it has a even weight. Okay. If you do something like this is a spanning tree. Alright. In each cycle C, all edges in C have even weight. In each cycle C in G, all edges in C has even weight. In each. The problem is this is a undirected connected graph. Okay. All edges have odd weight, but this in each cycle C, either all edges in C have even weight or all edges have C in odd weight. So here everything should have, but when it is even, you are not having any problem, right? Here is your answer. Thought of D, yeah. Right. In each cycle C of G, either all edges. If you look at this, right, all edge, okay, you didn't make a logical inference. This has odd weights, but the MST, every MST has even weight. So this is false. So now what we need? One, two. If you take the graph as MST itself, then it can have both even and odd. Okay. Think of counter examples. This is a undirected graph. I didn't think of these things. If cycle is there, yeah. If you do something like this, right, then this will be even, but this will be odd. So you will get controversy. D is the answer. Yeah, that analysis we got it. And I got this one right. We need to know about total orders. Diagrams. Partial order is reflexive, antisymmetric, and transitive. Okay. Not all pairs need to be comparable. 1, 2, 3, 4. 2 and 4 are comparable, but 2 and 3 are not. Every pair is comparable. Okay. One and two are comparable. Got it. 1 and 2 are comparable like this. Compare 3 and 2. Okay, 1 must come before 2. 3 must come before 2. Okay, that is how you compare. And okay. Count each total order is a topological sort of the Hasse diagram. Minimal elements. Must keep 1 before 2 and 3. Okay, so topological sort is a new concept. What is that? Is an order in which vertices of a directed graph for every directed edge u to v, vertex u, way to line up elements so all precedence constraints are reflected. How many topological sort does the DAG of P have? Okay. So let's say we have edge between 1 and 2, 2 and 3, 3 and 4, like an N, like a N shape where 1, 3 are below 2 and 4 are above. So how to find total number of topo sorts? So here 4, see, and 1 must come before 2, that is a constraint. Right. Chain case 1, 2, 2, 3, 3, 4. Okay, people, I will come back for this question later.